So first, I just want to point out why this one goes Markovnikov, or why the bromine adds to the most stable. And it's all because of our carbocation. Like, the hydrogen's adding first, right? But when the hydrogen's adding, we're also forming a carbocation. So the hydrogen goes to the least substituted carbon, so the carbocation can go to the most stable. Let me say that again. The hydrogen goes to the least substituted, so the carbocation can go to the most substituted, or the most stable. That's why the hydrogen goes there. We're always dictating where our carbocation is. And then the bromine is adding second, and we get this guy. It's not so much that the bromine cares to be on tertiary, it's just the fact that that's where the carbocation is. Okay, I think that's an important distinction to make. So the anti-Markovnikov, so this is Markovnikov. The anti-Markovnikov, I don't know if you've looked at it all in the book, but we're adding HBr, but we're adding peroxides to it. And these R's can be anything. They can be a methyl, they can be an ethyl. The R's is the carbon chain. So a peroxide is something like this, where it's two oxygens bound together.
Okay.
In biology, our oxidative, or ROS, these peroxides become very, can cause problems in our body. So you might learn about that. And then what it produces is a bromine. It puts the bromine on the least substituted position. So you might be thinking, oh, it somehow makes the bromine want to be there, which is how I thought about it first, but that's not the case. So the first step in this mechanism, just like, it's a lot like the free radical of bromine adding to an alkane, where UV light comes in, or maybe UV light doesn't even, but the peroxides split. So we get a free radical peroxide. It's the first step. And then that grabs a hydrogen from our HBr. Okay? So we're left with a free radical bromine. So this free radical bromine is what's going to add to our chain first. Notice here, the hydrogen added first. Here, in this mechanism, the bromine is adding first. So I'm going to flip our molecule around. And so it is going to bind with one of the electrons in the double bond. The other one goes to a carbon. And so the free radical wants to be on the most stable carbon. So that's why the bromine is adding to the secondary carbon.
Say that one more time.
Because when this free radical bromine is adding, it's going to take one of the electrons from the double bond. The other electron needs to go to a carbon, so we're going to form a free radical carbon here.
Okay.
And since the bromine's adding first, the free radical wants to be stabilized. It's just like a positive charge. So it wants to be stabilized, and so it goes to the most stable carbon, putting the bromine on the least substituted carbon. Here, the hydrogen added first, so that's why when the bromine added, it added to the tertiary. Here, the bromine's adding to our alkene first, so that's why it's going to the secondary, because the free radical wants to go to the most substituted. And then this free radical is going to grab a hydrogen, and then we form our product.
So the oxygen steals the hydrogen, so it can't bind first? So
bromine, you think of it in the way it's catalyzing it by making the free radical bromine. And this free radical bromine is very unstable, so it wants to react. So it's going to react first.
Gotcha. Okay.
Because these peroxides are very reactive. So you would think, oh, there's HBr, maybe some of it would be during this process. I don't think that's the case. I think, this takes a little bit longer where this is like splitting and then stealing that hydrogen really fast. We have a lot of free radical bromines. So they're what is